Hello, peoples of YouTube. It's me, your favorite YouTuber. Kidding aside, a while ago I made a video about repairing move videos, MP4 videos using a hex editor, the HxD hex editor. And since then, I've been contacted by people with the weirdest questions. They think you can just flip some hex values and make videos play again. Now, I demonstrated that sometimes this is true, but people expect me to give, they ask me, I have this corrupt video, here it is. Change the hex so it plays again. Of course, repairing files with a hex editor only takes you so far. You can often repair structures, pointers. You can try to determine if pointers are correct and if they're not correct. Try to determine what they should point to and then change that. That can be done sometimes. But often it's not that simple. So, and this is why I will want to demonstrate this practical case. This is about a USB flash drive which contained wedding videos. And it's years old and no one has looked at it, and now all of a sudden after a few years it turns out that when they view the USB flash drive in a computer, it still lists the files, but they can be played. They cannot be played. And I have one of those videos here because I don't want to see all videos in those cases because it's a lot of work. So then I'll ask, okay, send me one. And then will assume that, depending on what I find, that this video is representative for the other videos on the flash drive. And especially since this is a flash drive, an older flash drive. And a flash drive, the data on a flash drive is stored in NAND memory. Now, without going too technical, it's the same memory as is used in SSDs and memory cards. But we can basically, if we simplify, see a NAND flash memory as a huge array of NAND flash cells, and then each cell can represent a 0 or a 1. We know this is not true with modern NAND because it can a single cell can represent several bit values, but we're gonna go with the simple variant just to make a point. So if we consider a USB flash drive a huge array of non-NAND flash cells, each capable of representing a 0 or a 1, then we need to think about how we store this value, the 0 or the 1, and this is by pumping electrons or extracting electrons from a NAND cell. And to read the NAND cell, we determine the number of electrons or the charge. And if the charge is above a certain value, we treat it as 0 or 1, or if it's below a certain value, we treat it as 0 or 1. This is arbitrary. We can say we want 8 electrons. Now, okay, basically we have 2 states, and then we can decide that this is arbitrary. If this state, it will be a 0 or a 1. But once we've decided if it will be a 0 or 1, it stays that way. So think of this as a cell. This little, I don't know if you see the mouse cursor. Can I draw? Isn't there a draw thingy with this recording software? Okay. Okay, so we have a NAND cell and we pump a number of electrons on it. If it's above a certain value, we'll assume it's 1. If it's below a certain value, we will assume it's 0. And the thing is, with NAND flash cells, the electrons escape over time. It's not a perfectly isolating thingy. So over time, electrons can escape the NAND cell. And if enough electrons escape the NAND cell, it flips the value of the NAND cell. Because, say, 8 electrons, the NAND cell is considered 1, and 1 electron escapes, and another. We end up with 3 electrons. And now the value of the NAND cell is below 4, or in our that's our threshold, and then so it becomes a 0. I hope you are still with me. I don't know how to explain it, but what we'll see is when I open the file in a hex editor, we'll examine some pointers. And there are strong indications that the values inside the pointer are not correct. And for example, a value supposed to be 1,4 in hex has flipped, is read as 1,6 in hex. And this is the result of a single bit flip. If this bit here flips from 1 to 0, instead of 16, we'll read 14. And in another location, we'll find that a value that's supposed to be 0 actually reads as hex 04. And this again is the result of a single bit flip. And so even though we can repair pointers so that the move file in the end is recognized as a valid move file, a playable move file, we will see that the footage is so is very distorted, and we may assume that since we can find 2 bit flips, likely bit flips, in just 2 tiny data structures, we may assume that there are bit flips throughout the file inside the video data, and this causes the distorted view. And this cannot be repaired. We cannot determine if a piece of video data is valid or not. We cannot determine what bit flipped, so we can never flip the bit back. And even if we could, we would have to do this for thousands or maybe 10,000s of, or hundred thousands of bytes. So I'm going to in HxD, yeah. So there's our file. There is our file. Now, just like in that last video, I went looking for atoms, and I will do this again. I don't have to perform a long search like the last time because I can immediately spot the F-type atom, followed by a little later by an MDAT atom. So basically I have got two of my root atoms, atoms, and what I would like to know is where the move atom is. Move, okay, sensitive, move, search all. This will take a while. Somebody explained the NAND cell thingy to me by comparing it to buckets. If we fill a bucket more than halfway, then it represents a 0. And if it's below halfway or empty, then it's 1, or the other way around. It just depends whether we agree if a full bucket is a 1 or if an empty bucket is a 1. And we can imagine with buckets that the water slowly evaporates so that a bucket that is originally 0 or 1, whatever we decide on, the level drops until the point we call it the bit value has flipped. And this is basically what this is an analogy, yeah, for a NAND cell where the bit flips because of charge leakage over time. Okay, it's finished. We've got a bunch of instances for where it found the string move, lowercase move. Now, if we double click it, it takes us there, and we can pretty much tell that this is a pure coincidental string of bytes. And if we translate it to ASCII, we see move, but that's pure coincidence, and there is more of those. Now we know that the move atoms can be either at the start of a video file or towards the end. So this is probably our move file, a move atom, and we see all these little subatoms, and we see the move atom branches into a MVHD and a track atom and a TKHD atom. So this is our move atom, I will assume. And we see the start occasion. Okay, this is towards the end of the file, where we see it here as well. Okay, I'm going to return to the header. F-type atom. Is this 20, 20 bytes. I am lazy, but I'm going to be lazy, and I'm going to do conversions in the little calculator so you can see it as well. Oh, I'm doing it the other way, the wrong way around. Okay, so this is a decimal value, so the length is 20 in decimals. I want to know what the length in hex is. It's 14, and that's is where we see our first bit flip. This is where I got this value, this example from. this is incorrect. So, because the correct value is 40 in hex. So I save that. And our next atom is the move atom. Now, if we look at the 32-bit size field, it says 01. And this means that the size of the embedded atom is too large to store in a 32-bit value. 32-bit. In a 4-byte value. I'm gonna just call it bytes, otherwise I always get confused with the bits and the bytes and the stuff. But so the 4-byte value is not large enough to store the real size of the embedded atom. So then if this is filled with 01, this means that we, instead of looking at that, we look at the 8 bytes following MDAT, and then we get this value. It's a big Endian, and if we look here, we can immediately see this cannot be right. If we look at size, if we look at the number of bytes inside the file, this is way larger, so probably something is wrong here. But with the size for the embedded atom. And we can, since we know where the move atom is, and we'll go there again, we can pretty easily determine the real size of the MDAT atom. This is the move atom. So, and 4 bytes preceding move is the size of the move atom. I don't care about it now, but then this means that this is all MDAT. God damn it. MDAT. And 1, 2, 3, 4, those included. And then we get the length of the MDAT atom. So in decimals, so let me see, 161824. My eyes aren't that good. 24 94 94 981, I guess, in X, and we get this value. Now, our embedded atom is here, and this is our 8-byte value. And we see our next, we catch our next bit flip in the act. This 04 is not supposed to be here. 3C 4 8 D 4. I mean, the value is correct, but this was supposed to be 00, but a bit flipped this bit. So 00 in hex became 04 in hex. 00. Now it's correct. Now I can save it. And now something happens. We immediately see that Windows start recognizing this move file as a move file, as a video file. the preview does not look encouraging. It's corrupt, but we'll try play it anyway. And is that all video data. Okay, now again, since we were able to determine 2 bit flips by examining in total 12 bytes worth of data, combined with the fact that the file was stored on an USB NAND flash drive of years old that hasn't been touched or viewed for years. My conclusion is that what we're probably dealing with is bit corruption throughout the and I mean, 4 bytes and 8 bytes we examined. We have 2 bit flips that we already caught in this tiny bit of data. So there's probably bit flips throughout the entire file, and this will make the file beyond repair, unfortunately. So we were able to correct the structure. I have another hex editor. I will open it in that, and then it has a template for MP4 and move. It recognized the file as a move file, and it applied the template. And we see it can parse the entire file, the structure of the file. So we did structurally repair the file, but unfortunately there's probably corruption throughout the entire file. So yes, a hex editor can be useful for repairing files, but no, a hex editor cannot repair each and every MP4 or move file. And then by combining findings and factors, like on a USB flash drive, years old, charge leakage, finding bit errors, 2 of them already in a tiny bit of data, our conclusion probably has to be that we cannot repair this file. I think I have covered everything I wanted to cover. Thank you for watching, for those who watched and watched all the way through. Don't forget to like and subscribe. It will help my channel. Thank you.